Okay, so let's quickly take up these questions. So whenever you're doing any types of questions like this, you always have to state your givens. So in question 1, we have the frequency, which is going to equal 60 hertz. And we have wavelength, which is equal to 25 centimeters. This poses a problem because if you note here, wavelength, change color, is in meters. So we need to convert 25 centimeters into meters, which will be 0.25 meters because there's 100 centimeters in a meter. And then we just need to multiply. So 60 times 0.25 equals 15. And then our units are meters per second. Okay, next, we're still doing the same two givens. So our frequency is 4.3 times 10 to the 14 hertz, so a rather large number. And our wavelength, in this case, is a really tiny number. So 700 times 10 to the negative 9, because they give it to you in nanometers, which is a really small unit. And then you have to convert that to meters, which, you know, you're dealing with a really tiny number here. So if 1 nanometer equals 10 to the negative 9 meters, then we're going to do 700 times 10 to the negative 9. Then we just multiply those together. It's 10 to the 14th times 700. Okay, and again, using brackets and your calculator, and hopefully you remember how to type that in using scientific notation from grade 9 math. You're just going to plug that into your calculator. And you get 301 million. Okay. Okay, so moving on. I asked you to complete this sheet. So I don't have it all filled in. There's just a few things I want to talk about on this sheet. The biggest challenge might have been trying to show this wavelength coming across the top of your worksheet here, getting smaller and smaller, and yet not changing the amplitude of the height of the wave. Clearly I fell a little short at the end here, so art is not my skill. So anyway, what you want to see is the frequency increasing as you go from radio waves to gamma rays. Okay, and then it asked for you to look for patterns. What is going on here as you go from radio waves to gamma rays? So if you look at the frequency, how many waves you fit in a given amount of space, you can see the frequency is increasing as you move from left to right, or as you go from radio waves to gamma rays. Wavelength is decreasing. Okay, so the amount of space between, you know, the top or the bottom of the waves is constantly decreasing as we move across. So the wavelengths are getting shorter, but the frequency of them is increasing. And energy increases. So as the frequency increases, the energy increases, which is important to note. So these two things go together, increasing and increasing. And the way I want you to visualize that is if we look at these types of waves, we can't see them because they're energy. And remember, well, I shouldn't say we can't see most of them. I'm going to get to the part we can't see. So this is energy. It's all around us. We can't see it. We can see what it does to some degree, but we can't actually visibly see it unless we're talking about a certain portion, which I'm going to get to. Now, radio waves, microwaves, are fairly, you know, they're not really harmful to us. And that's because if we look at the frequency, Okay, they're so far apart. They're big and long. So when you think, sure, they're bombarding us all the time, but not at a very high rate. Okay, so the frequency is very low here. So we consider those harmless, right? We're not worried about the radio waves. And cell phones do lie in this area as well. So we don't really worry about that energy hurting us. Infrared waves, as we approach here, we get to infrared rays, are kind of interesting. We can't see infrared rays. However, some animals can. There are insects that can and reptiles that can. So this is a type of energy that they can perceive. Their brains can perceive it. They see it. We don't, but we do have special goggles that do allow us to see it. And after infrared is ultraviolet. We can't see that either. Okay? That's typically, we're starting to, our frequency, the amount of waves we get in a given amount of time is increasing. So by the time we get to UV, ultraviolet rays, they're bombarding us a little harder. So, we're kind of in this section here, and you can see they're starting to get closer together. So over the long term, ultraviolet rays can actually damage us because we know that if we get too much sun, they will literally start to rattle our DNA inside our cells and cause breakages, which if they land in the part of the DNA that controls the cell cycle, we all know that can cause cancer. So as the frequency increases, the amount of energy increases and the amount of damage it does increases. And if we look, I've put the visible light spectrum here because it's really not included in here, but that's really what we're going to be focusing on. In between infrared and ultraviolet, neither of which we can see. Actually, there are some insects that can see ultraviolet. We can't. But in between those two types of waves is what we call the visible light spectrum. And we're really going to be doing most of our focusing on that visible light spectrum. So if you look down here, I have what is the visible light spectrum. We call it Roy G. Biv. Red, orange, yellow, green, blue, violet light. Okay, so this is types of light. They all come together to make white light, which is what is bouncing off everything around us so we can see. That's what's coming from the sun. So this little section called visible light, which is in between infrared and ultraviolet, is something our brains can perceive. So it's energy we see. It's actually our brains that see it. So we can see this little tiny section of this electromagnetic spectrum, and we call that visible light. And if you look at what comes before and after it, it makes sense. Infrared comes before red. We can't see infrared. Some things can, but we can't. But we can see red light, orange light, yellow light, green, blue, and violet. So we can see what comes after infrared. Then we get to ultraviolet, which comes after violet. We can't see it again. It's a type of energy our brains cannot perceive. Some insects can, but we can't. So in between infrared and ultraviolet is this section of energy that we can actually see, and that's why we see everything around us. But again, it's just certain wavelengths of energy that we can perceive. And your focus tomorrow, when we look at the additive color theory of light, so we're going to be looking at the different colors of light that make up white light, that's what you're going to be looking at, is the visible spectrum of light. Please tomorrow do not get light colors mixed up with pigment colors. I know when you were in kindergarten, you mixed colors together. You mixed your red and your blue and you got purple and it was amazing, and you mixed your blue and your yellow and you got green and you were like, wow. Mixing two different colors of light doesn't work the same as mixing two different colors of pigment or paint. That is totally different. So you're going to get some surprising results tomorrow when you combine different colors of light, things that you're not expecting because your brain is used to mixing pigments. Okay? So this little section, so if you could on your diagram here, on your spectrum, if you could fill in, I had to go, search my 10-year-old's drawers and find some colored markers. Hopefully you have got something colored at home. I understand if it's still at school, but it's nice to include the Roy G. Biv. So you have on this sheet, oh, and right smack in the middle here is the visible light spectrum that we can see. And then beyond ultrawave, we have X-rays, and now our frequency, if we look at our frequency here, is getting, you know, higher and higher. So the waves are getting closer and closer together. That means they're bouncing off you and your cells and your DNA even more, causing more damage, which is why we always limit the number of X-rays we get. Pregnant women are not supposed to get X-rays. We don't want to be bombarding the fetus's cells with this kind of frequency of energy. We don't want to mess with their DNA. And then, of course, at the very end of the spectrum is the gamma rays, which are really, really dangerous, and we don't go anywhere near gamma rays because we know that they are very damaging. So try and fill in, if you can, that visible spectrum, the different colors, and note that is our focus right here for tomorrow and early next week. We're going to be looking at that visible spectrum and the way our brains perceive it.